Alright then, hello everybody. This is my first live stream on Instagram, and I thought it would be a good idea because I haven't done a video for a while, and I appreciate that everybody's been waiting for me to update on the progress of the project. There is a specific task I need to do today, which is to rebuild this board, and I'll talk you through that in a little bit. But just really to get started. Hopefully everybody can hear what I'm saying. I am kind of in this orientation. I'm trying to do this in landscape, really, because I'm going to put it on YouTube afterwards. So hopefully that's not going to be too disconcerting for everybody. And yeah, let's have a couple of minutes and then we'll make a start. Trying to fit everything I can in the screen so you guys can see everything. What have we got? A bit of this, a bit of that, a few of them. So I'm going to be checking for comments every now and again. But I can't see everything all the time, so apologies if I miss anything. So here we go. Hopefully everybody who's on understands what it is that I'm building, but in case you haven't seen it before or you are in any way confused, I'm building this guy, and I'll put him on the desk so you can see. So this is a Raspberry Pi and Arduino powered robot. It is fully autonomous. It will, when it's finished, it's going to look a little bit like this, but obviously I'm trying to tidy everything up as I go. And yeah, the goal has been the entire time to try and build something that is going to work by itself without any interaction with controllers or anything like that. I get a lot of questions around mobility and that kind of thing. It's designed to be a desktop component. It's designed to be a desk buddy. It's not designed to walk. However, I've been making changes over the last version to kind of move us in that direction a little bit more. So, for example, for the first version, the legs were too flimsy to be able to actually hold weight on one leg, whereas with this one it's a lot more rigid. Also, you have some articulation at the hip joint as well, so that you can potentially position it in the middle of the center of mass, so that you can actually have it balance on one foot. If you made some further changes to do that, you would have to add a further servo here to handle that articulation. But yes, it's not in a position that it's going to walk. We're not looking to do that for this version. Having said that, it's all open source. So if that's something that somebody's interested in doing, then they can feel free to take those designs and work on them, and I'd quite happily integrate them if that was ever something that got working. There are, however, 1,000 things that I want to do before I get to that point, so that's not going to be a focus for now. Anyway, so we have the head. Head has a few servos. Servos move the head up and down, and also turn left or right. There was originally a third servo, which would actually make the neck kind of tilt down so you could fold it flat against the body, but I removed that for this version just because it wasn't really necessary. There wasn't really a lot of use, and it made the design much more complicated. There is a Coral USB accelerator on the top, and that is for kind of object recognition, face detection, that kind of thing, and it just plugs into the Raspberry Pi mainboard on the back. So that head component is quite simple. You have a boost or a buck converter which just takes in any voltage. I've got it kind of rated up to 24 volts max, and it'll convert that to the 5.1 volts that the Raspberry Pi needs. So it means that you can supply any kind of voltage to the head up to 24 volts. You don't have to worry about giving it a specific voltage, which is quite cool, and it means you can run it independently of the body as well. So these things can be detached, and then you can plug another power supply in if you want to, and detach the neck and all of that sort of stuff. There's also a motion sensor, there's a couple of microphones, MEMS microphones in there as well, and then a custom PCB which you kind of can't see in this, that the header pins there are actually part of the custom PCB that plugs into the Raspberry Pi as like a hat, and that just allows for all of that logic to happen. And then the only other thing is, coming out of the Raspberry Pi you have the power going in, and then you actually have a serial connection as well, so that you can communicate with the Arduino in the body, and that's the thing that we're going to focus on today. So these wires are just for the servos. I'm going to disconnect those because I don't think I need those for what we're doing, and then we'll just put the head somewhere else and we can keep focusing on the next step. So I've had a few different versions of the board that controls the legs and the neck as well. So all of the servos are actually controlled via the Arduino that's in the body, and that's this here. Originally I had this version. It had a relay that went on the top there. I've just desoldered that because I was going to keep it for another project. So you would pass in the power, and again that was something like up to 20 volts. And then you had two smaller buck converters, one for the Raspberry Pi, which was on kind of there, and that fed to these pins, which were those connections that we just talked about to the Raspberry Pi, and then the other one was actually to power both the Arduino and the servos as well, and they would go through the relay. So the Arduino could turn the relay on and off, and it meant that if you turned it off, then all of the servos would lose power, so therefore you could save power. You wouldn't have to worry about burning through power just holding the servos in position, but the Arduino was still powered, and that was quite cool. But the problem with that was that when you enabled the relay, there was a spike in the power that kind of was a brownout effect on the Arduino, so therefore the Arduino would reset, which would therefore reset the relay, and you would get into a bit of a loop. So that wasn't a fantastic approach. I also found that I didn't really need this, and I didn't really use it, and in the end I just made it so that it was constantly on while I was using the robot, because let's face it, if you're using the robot, you're going to want it to animate, you're going to want it to do a few different things. So, new version of the board, I wanted to upgrade these, not because there's a problem with them. I haven't actually had any issues with power delivery from these two buck converters. The problem that I've had is that if there are issues, I can't swap them out. And you can see here, since I upgraded the head so that it has its own buck converter, I've just had to wire this straight over the top of that part of the PCB, which means that's a complete waste of space. Similarly, I did have a fuse in place, which I don't really want on this board anymore. I want to put it somewhere else. And I just thought we could do with a little bit kind of improvements on the design. And then finally, what I thought was a good idea of lining all of the servo header pins up in the middle actually meant that their pins had to kind of come over the top and into here, which means that there was a lot of extra wiring running out through the board from the center point, which is really hard to access. So you'll see from comparison here, the new design actually has these 90-degree angled header pins, and you can take the legs, which are 3 servos each, and plug them in on one side and then the other leg in on the other side, and then the ones that come out the top here are actually specifically for the ones that are coming up to the neck and the head, and therefore need to be heading in that direction. So it means the whole thing can be a lot more compact, and we don't have any real problems there anymore. So that was the old one. This is the one that was running in the smaller robot that I did, which was version 2, for those of you who are keeping track. And then I did have it in this one, but again, it took up so much space, it just meant that this whole body area was a lot bigger than it needed to be. So the new goal of the new PCB is to try and slim everything down a little bit as well. So let me put that off to one side. So there's a few different things now. If I move him to one side for a second, what I have got, he doesn't want to stand up anymore, that's useful. There you go. What I have got is a few different choices for power. So he has the ability to accept USB-C. I do have a power delivery board, so you plug your USB-C in. I've set it to 12 volts, so it'll take 12 volts power in, and it can power itself indefinitely from that, as long as there's obviously power from the AC. But I also wanted it to be mobile, So therefore I also have some 18650s, which are kind of those large AA looking things that are bigger. I have 3 of those, which again is about 12 volts. And what you can do is there's a switch on the back, so you can switch between battery power and mains power. I don't have a charging system in place. I just haven't been able to get that working in a way that I've been happy with, and I haven't worried about wires coming loose and so on. So that's kind of future versions. But what I wanted to do was have a system so that I could pass the original 12 volts from either source up to the Raspberry Pi through those wires that you saw, but then also have the ability to power the Arduino and the servos. And if there are problems in the end with the smaller buck converter not being able to deliver the right amount of power because the bigger servos now, there's a lot more draw. As it starts doing more complicated things, it might be that it isn't suitable. So what I wanted to do was have the option to really isolate that and make it so that I could switch between different buck converters depending on whether one of them didn't work or whatever. So I ordered a few. So this was the original one. This one, I can't remember exactly which one's which, but I'll post the specs on the Instagram channel. This one's like the next one up, and I think this is the same as what I've got in the Raspberry Pi head component. That all works really well. You can use a screwdriver on the potentiometer just to adjust the voltage, and then once it's set, you don't have to worry about it anymore. Any voltage that you pass in up to the maximum allowed will result in a stable voltage coming out on the other end. So it's not that if you pass in 12 volts and then change it to 20, you have to fiddle with anything. It'll just keep it at the output voltage that you've set. And then the only other thing was this one, which is a slightly beefier version of this. I did a bit of research to try and find out what the options were. Ideally, I guess I'd like everything to be as small as possible, but I also want to make it so that if I have problems, I can narrow down the scope of the issues, and really the difference between the size on those two is so minimal. So I figured what I'd do is I go for this one in the version that I'm building, and then pass that power onto the Arduino, and then that means that I don't really have any issues. So we're going to discard these, but it's just to talk you through that they exist and there are options, and if you're building something yourself, I haven't had any problems with that tiny one, except for, not being sure whether some of the power issues I've had, for example, the brownouts on the Arduino when you start the relay and that kind of thing, that might have been because of that, and I haven't had a chance to test. So I thought if I go for the biggest one possible, at least it might alleviate some of those issues. So on here, if we look down the back here, what we've got is, this was originally along here, which is why it doesn't, which is why it doesn't fit in the smaller area. But you can see we've got the switch there that picks between the USB-C input and the battery. And then I had another hole because I had a switch to enable that relay, which obviously we're not using anymore. So you can see those components are in there. We're going to take that out in a second because we're going to use it in the new version as well. And then that passes power up to this ridiculous little board that I kind of threw together to try and test it. And as you can see, it's the same buck converter that I've been using in the other areas. I just tried to split it out a little bit. And I had been using dupont connectors throughout the entire project. They're used in the servos anyway because that's what they're shipped with, but I've been using them for everything else as well. And it has been working all right, but the problem is it's quite bulky, as you can see. Just for connecting two wires, you need quite a lot of space. It's quite difficult, not very flexible to move them around. So we have this one coming up from the from the power input switch down there, and then coming out at that same level. So what this will do is it'll take the input voltage and then output 5 volts on the other side for the Arduino, and there's 5 volts there as well. The problem really here is that I want to monitor the voltage. So I want to do that in a couple of ways. I have this on the front, which is the just a play voltmeter, and it takes a positive and negative connection in. So I've ended up having a connector there, which is again another dupont connector. But then I also wanted to pass that voltage through to the Arduino and use a voltage divider to tell the Arduino what the voltage is so that it can shut down, or it can tell the Raspberry Pi to shut down if the battery gets too low. We'll talk about that later on because that's something that I want to build as part of the stuff that I'm doing today as well. But yeah, you can see it starts to get a bit messy and it starts to get a bit complicated for the space that we have. And then I did print this board, and it's better than the original one was. It's better than the green one, but the problem that I've got is it just doesn't quite do what I need it to do, and I made a few mistakes. And I'll talk you through those because I'm quite happy to admit that this is not really my area of expertise, and I'm trying things out as I go. So you can see we've got the Arduino. We've got some headers to connect it to the programming chip, which is this. So if you're not familiar with this, things like the Raspberry Pi Pico, I get that out and show you, and other versions like the Arduino Nano and the Arduino Uno and that kind of thing, they will have the programmer included in the board. So you plug your USB in and you connect it to your computer, and then you can program and add the code. For the Arduino Pro Mini, that's not included, and that's why you don't have that USB adapter and so on. What you need is this board, which I can't remember the name of, there you go, in order to connect it. So you take the wires, you have the RX and TX, you have 5 volts, you have ground, and you feed those into the header pins on the Arduino. You also have this one, the yellow one, the DTR is actually to kind of reset the Arduino at the point that the upload starts. So some of these won't have that pin, and you actually have to manually press reset, and the other ones do, and it does it for you. So you plug those in, and then you're allowed to program it, which is great, which works really well. It gets complicated though if you actually have the board already integrated, because of course all of the power for the servos and for the Arduino is going to be shared on the board, and if you try and plug this in to your laptop through your USB on your laptop, it's going to try and power the servos through the laptop, which you don't want. So we've got a solution for that in the next version as well. So yes, I'm kind of taking you all over the place, bear with me. What else? This is the voltage divider circuit that I was talking about, which is just 2 resistors, and the idea is that you connect those 2 resistors between the input voltage and ground, and then where they are connected, that midpoint, actually I've got a diagram, let's show you the diagram, that would be better. So yeah, circuit diagram, you have got, maybe I'll do it that way, maybe depending on which orientation you've got. You've got an input voltage, mine is between 5 and 24 volts. I then have 2 resistors of certain values, and based on those values, the output at the midpoint is something that is less than 5 volts. And that's quite important because it's fed into an analog in pin on the Arduino. And if it's more than 5 volts, it damages your Arduino. So if you're passing 24 volts into your Arduino pin, it's going to do some damage. So you need to have a voltage divider of certain values in order to make sure that you're only ever passing a maximum of 5 volts. And then at that point, the Arduino can actually go through and understand what that voltage is. So as the battery level drops over time, the reading on that pin will go down, and you can use your code to understand whether you need to turn the Arduino off, whether you need to flash a warning, whether you need to turn the Raspberry Pi off or disconnect the power or whatever you might want to do. So it's a really useful thing to have. So I'll talk you through how we build that on the board as well. So moving on from that one, everything else is kind of okay, but it was just a bit messy. And then the other thing that I didn't do was I think I forgot to connect the grounds. And if you ever have multiple circuits running and potentially multiple power sources, you always want to have the grounds connected, otherwise you get unexpected behavior. And I think in this case I actually forgot to connect the VCC as well, so I had to manually power the Arduino via these connectors, which obviously was just messy. So it all ended up being a bit of a farce, really. Fortunately, JLC PCB comes along and offers PCBs for a couple of dollars. And therefore I printed a new one. So that's what I'm going to be building today, is the new board that I've created, which is very similar, but I've added a few things and I've fixed a few things. Now there are still problems with this one, so I've got another version that I'll do later on, but I just want to get this done, so I figured I might as well make a start. Excuse me. Let me just check the comments. No questions yet? Okay, fine, good. So here we go. So this board works in a very similar way, and I've got another one here that I've just started soldering things onto to save a bit of time on the stream. So you can see there is a space for the Arduino Pro Mini, and the headers are all in place there. There's also another one that's overlapping, as you can see, and that's actually for this it's the MPU 6050, which is like a motion and orientation sensor. Now what I'm going to do is attach that underneath. So the Arduino Pro Mini goes on top, motion sensor goes underneath, and then they're connected just through a couple of pins. I think the I2C pins, and then the voltage is also sharing the same lines. And it means that if I want to work out whether the robot is stable or not, then I can do that with that. So if you put it on a board and then you tilt the board, or if you put it on an uneven surface, it can adjust the leg positions based on that to stay level. So it's a useful thing to have in place. I haven't put any code in for it yet, but it's something that I did want to add, so I figured I'd put that in the board. But just in case you're confused about why it's overlapping, it's because one is going on the bottom and one is going on the top. That said, I'm probably not going to put that in on this stream. I'll do that some other time, and then I can test it out separately. So other changes, we have JST connectors. So the difference, there's a few actually, and it's worth explaining how all this works. DuPont connectors, as I showed you, are pretty good. They're pretty kind of easy to use. The only problem with them is you can't enforce the orientation. So if I have servos, for example, and I want to connect the servo to the header pins, if you connect them in the orientation that they work, that's completely fine. If you turn it 180 degrees, it will still allow you to make that connection. Now for servos, apparently that doesn't matter too much because the voltage is in the middle. So all it's going to mean is that the signal pin and the ground is going to be swapped, which isn't really going to do any harm. You'll just find that the servos don't work. However, if I was to do that for literally anything else on this project, I could end up causing some quite bad harm, because I could maybe pass the wrong voltage through to the Arduino and fry it, or I could, do all kinds of damage. I didn't want the risk of that, and I'm constantly taking this thing apart. So what I wanted to do was use a connector that did enforce that orientation. So, for example, there are different kinds of JST connectors. I'm not an expert on which ones to use. These ones take a wire and a wire, and therefore you can disconnect them, and you can see they fit together there in one direction, one orientation. If I try to put them in upside down, it won't allow me to do that. And so it means if I have a wire that I need to quickly take apart and connect again, it's a secure connection, but it won't allow it to be changed and the polarity swapped or whatever else. But what we're using on this one is actually for the board connection. So the pins spacing is the same as the DuPont headers, so it means that you can use either. And then what I've done is I've ended up with one that is pointing directly upwards here for the connection to the Arduino, and then I have two that are 90 degrees that connect to things within the body. So I didn't want them sticking up, because then it's got to come out around, and it makes it much more complicated. So the idea with that is you have these ends, and they have pieces of very tiny little pieces of metal that you crimp around the end with a tool. And I have the tool actually. So it's very fiddly. I had a hard time learning how to do this. But you take this, you feed the wire into the end of that. You use this crimping tool to squeeze that onto the wire, and then once it's clipped, that's it in place. And then you push that crimped end into the hole, and then that means that you end up with something that looks a little bit like this. And it just means that once you've done that, that should be relatively secure. You shouldn't have any problems with those wires slipping loose. And now when I connect this, if I was to try and connect it in the other orientation, it wouldn't allow it, but it's an easy, secure connection otherwise. And you can see on the board here, the 5 volt is the bottom pin relative to me. So therefore you can see that's the way that it's oriented in here. Ground is in the middle, and then the third wire, although this is a servo wire, is the original voltage. And we're only using that for monitoring, so that the kind of thickness isn't so much of a problem. And what it means is if I was to connect it that way around, it would probably fry a lot of stuff, because the 12 volts wouldn't be accepted by any of the components. I'm not sure if the Arduino could handle it, but I doubt it. So good to keep it safe. So that's the plan. So I've got a couple of those wires. The 3 elements on the side here are voltage in with the 5 volts and the original voltage. I've got a connection going up to the Arduino, as I've mentioned, so there's a positive and negative of the original voltage, and then I've got the 2 serial connections, so the TX and RX there. And then the only other thing which you can see here is this voltage out, and currently what I'm using that for is the voltmeter on the front of the Arduino, sorry, on the front of the robot itself. And so when you plug that in, you should see the voltage once the power is turned on, so we can keep an eye on it. And eventually the Arduino will manage that itself. But you know, if something goes wrong and it crashes or something like that, it's good to see that I'm not running the batteries down too low. And that's basically how that works. Let me just check and see how you guys are doing. It's not showing me any questions, but I am seeing messages pop up, so apologies that I'm probably missing some things here. Let me have a quick look. You're actually balanced if you're interested in how this setup works here. I'm really doing this low cost. So you're actually balanced on a ring light with a 3D printed mount that's going into an IKEA pegboard alongside the tools that I've had time to 3D print and attach. So you will notice you're bouncing around quite a lot when this when I look at things. So somebody said, for powering the servo, which step-up converter do you use? It's actually a step down, so it's a buck converter rather than a boost converter, and it's the ones that we've just I've just shown you. So let me have a quick look at this one. I don't have the details. I did plan on putting them, making a post on Instagram to show you the spec for all of these, because it's useful for me for reference as well. But yes, I will do that, and then that way you're seeing what I see, and you've got access to all that information. Okay, cool. So that's the JST connectors. As I say, I did quite a lot of this off screen just to try and save a bit of time. And then for the headers that we have, it's the same setup. So you've got the pins for the legs on either side, and because I've turned that 90 degrees, they are going to be connected in a slightly different orientation. So the top row is all ground, the middle row is all the 5 volts, and then the bottom row is the pins, and those individually go to the signal. Those individually go to the correct pins on the Arduino, and you can see in here that I've labeled them all. So the orientation's a bit strange, but D 2, 3, 4, 5, 6, 7, 8, and then 9, 10, and 11, and that's just because of the way that the wires are actually connected on the board. So that's that, and then the final things are around the voltage divider and the bridge connector. So let me point with something. So you can see on here there's a couple of pins that are blocked together called bridge. The idea behind that one is that if you put a header that allows you to connect those 2 pins together, it will power the Arduino through the 5 volt input. If you don't do that, it will disconnect the power from the Arduino, but the servos will still have the power coming through. The reason why that's important is because, as I say, I don't want to power the servos through the laptop if I'm programming it, but I do still want to test. So I can remove that header, and it means that I can power the Arduino through the connection to the computer, and then I can power the servos through the USB-C or the battery or whatever's coming in through that 5 volt in. So it just makes that isolation a lot easier. You'll notice there isn't a one for ground because you always keep the grounds linked, but it just means that I get that kind of safety net, that I know I'm not kind of powering anything that I shouldn't be. It also means if in future I want to use this board and pass in more than 5 volts, I don't have to completely rebuild the board. I can maybe just change the voltage that's going in to supply servos that take a different voltage, leave that bridge pin off, and then I can use the Arduino Pro Mini and just power it manually through a different connection. So it's quite cool, it's quite useful from that perspective as well. And then you'll see here there are 2 spaces for resistors, and that is the voltage divider space that we were talking about before. And I have a couple of those ready to go, so I'll talk you through all that as well. I've got a question. It's the same question. Okay, I think we're good. I think we've got that one. So I'll get rid of that as well. A couple of things in terms of the setup I've got here. I have a fan with a filter for the soldering, and that's pretty important. If you guys don't have that already, it's a good thing to have if you're doing a lot of soldering. I did put off getting something like that for a few years, but I actually salvaged this out of an old printer and then got some of the proper filter that you need. So all I've done there is connect that to my benchtop power supply. It's 24 volts, so it means that it just sucks the fumes away and I don't have to worry about dying quite as much, so that's good. Right, is that everything explained? I think we're good. So what I'll do is I'll just work through this and talk you through the process as we go. And as I say, if you've got any other questions, just shout up. Nice. So someone said, according to the data sheet, you can power the Arduino with up to 12 volts and you use 9-volt batteries. Yeah, exactly. So I typically try and make sure that I'm not passing too many different voltages around a project because it starts to get confusing. I tend to work on these projects late at night and at the weekends when I get 10 minutes here and there, so I don't want to have to be constantly thinking, am I passing the right thing through here or am I going to fry something? I really want it to be straightforward, and that, again, that's why we've done this kind of safety net, just to make sure that there's no issues. So I wouldn't be passing through 12 volts to the Arduino directly from the batteries or directly from the power supply, because I guarantee you I would forget. And then I would change the USBC power delivery to pass through 20 volts and it would fry it and I would be down, weeks work. So that's that. Cool, okay. Then what I've got is some helping hands. By the way, if you're ever in the market for helping hands, don't buy this kind because it's awful. It is something that I've had for years, but they scratch the boards because they don't have anything wrapped around them, and you're really limited on how you can do this. There are proper ones you can get for mounting PCBs while you work on them, and there are also ones that are much more flexible for actually holding wires together and things like that. So do your research. I'm going to put the fan on, just check it's going the right way around, and then we'll start working through everything. So, yes, one more thing, mistakes. I made mistakes on this board as well, but fortunately I've managed to kind of rectify them. There was a couple of things. You'll notice there's a big scratch here, hopefully that's in focus. That's because I didn't notice, because the top layer of copper covered the bottom layer on the software that I use, but these two traces were touching, and therefore it was sending, I think it was sending 5 volts through to the TX pin or something like that. Something was going on that shouldn't have been. So I've just scraped that trace off. I actually made mistakes with all of this, but it kind of wasn't my fault, because on top row here, what you do is I use fritzing, which is not the most recent thing. I know there's a lot better ones, but I use what I know, and I've been doing this for a little while. And the part for the Pro Mini is something that you download and you drop in and then you use it. And as you can see, all of the individual pins are labeled, but along the top here it's labeled them incorrectly, and I just didn't pick up on that. So the actual labeling should be ground, VCC, and then RX and TX, but they've swapped them over, or they've mirrored them or something. I think they're mirrored. So the problem with that was that I just took the assumption that that was correct, had the board printed, and then when I plugged it in I realized it was going completely wrong. And I only noticed because I couldn't program the board while it was attached to the PCB. As soon as I attached it, it started working again. So yeah, I've had to ignore all of that. So you'll see here, I did originally have this really obscure kind of double-sided extra long header connector, and that was going to connect to another one of these female connectors in here. But because of that issue, I've decided just to bypass all of those pins, and I'm going to print another board for later on, but for now I guess it's fine, I can work around that. I've just had to add a wire to connect this ground to the ground that goes down to the power, because that was one of the ones that I scraped away there, because originally it was going to be connected to that pin, which should have been ground as far as they're concerned. So yeah, a little bit of a mistake. All of this stuff is available on the GitHub repo, which you can get by looking at the profile on the Instagram account. So if you're interested in printing the boards, you can order them. I do recommend JLC PCB just because of the cost, and the service is really good. The delivery time is quite slow, which is the only downside, but it really, you know, it's easy enough. This is the third version, if you include the green one, and I'm obviously going to be printing a fourth, so yeah, it's easy enough to do. But yeah, see what you want to do. If you are learning, there are more modern tools in fritzing, although I do think it's still actively maintained, so there you go. Cool. So what I've done is I've already soldered the pins that I'm going to be using, and obviously not all of them are in use, and I typically don't solder the ones that aren't in use just in case I need to change something, or maybe I want to take it out and solder a wire in there. The only thing that hasn't happened is the A4 and A5, and they're a bit of a strange one because they go kind of, they're not in the rows that all the other pins are because there isn't room on this board, so they've kind of put them recessed a little bit into the board, which makes it really difficult. And it also means that if you're trying to use a breadboard, the spacing doesn't work and you can't connect them because they're going to be sharing rows and they're slightly offset, and it's all just a bit of a mess. So that's part of the reason why I ended up with custom PCBs. Now they aren't in use on this one until now because of the motion and orientation sensor that we've got there. So yeah, but I think we'll leave those off because, as I say, I'm not going to be programming that in today. I just want to get the power working. So let's jump in then, and what I'm going to do is I'm going to take my project apart a little bit. So hopefully you guys can see this. I've got this header. I'm just going to disconnect these first of all. We'll be done with that. I'm not going to use that one again, so I can take that off. Oh yeah, and you can see I also made a mistake on this one with the voltage divider, because I think it was connected to the 5 volts, which obviously was useless because then it would have just read 5 volts all the time. So that's what late night changes does. So let's see, we're stuck on something in there, I think, or I've got it connected somewhere else or something. A bit of a fiddle. I've made this door so that it disconnects at the back here, so you can actually get in and get access to things, and it's probably that's connected. And these are the 18650 batteries that I talked about. I mean, they're really good, they work really well, and I feel a bit safer with them rather than LiPo, which I do have a LiPo as well from the previous version, but it just means you can pop them into a charger. And this is the switchboard. And again, I'm going to have to reprint this, but I'll do that once I've got everything sorted. So you can see I've just got that USBC power delivery board there. You hold this button down and plug it in, and then it allows you to select the voltage. And then when you disconnect and reconnect, it will have remembered that selection. So as I say, I've got it set up to be 12 volts now. And then it also has a connection to the battery, which we've just disconnected there. And then this is the output line. So this is the one that we're going to pass into the buck converter in order to make this work. So that's that, and then I'll leave all of that connected because I might want to refer to where that is. Get him out of the way, and then we'll make a proper start. So the goal with this one is I'm going to have this guy, and I'm going to have the input coming from here, and then I'm going to have the output obviously coming from the other side. But the key thing is I also want this yellow wire, which is a servo signal wire. I want that to connect to the input as well, just so that we have a read on that voltage too. So I'm going to have to do a little bit of kind of work around making that happen. So let's disconnect some things. So what I'll probably do is just shorten these two and have it so that that's connected directly underneath, and then they're connected over to the output, and then that way everything is still in place. But if I want to swap this out, it's just going to be a case of disconnecting that wire, making a new one with the other one, and then connecting that in as well. I'm not so bothered about about having a JST on here. It doesn't really fit very well. I could potentially use some of those wire-to-wire JSTs, but it's all extra space and it only takes seconds to desolder a couple of wires, so I'm not so bothered as far as that goes. So yes, let's do that. We've got that one, and then I just need some tools here. Now apologies if this goes out of frame at any point, because my desk continues a lot closer to me than you guys can see, and if I extend that mirror out, that ring light out anymore, I think you probably find that it wobbles a lot more. So we'll just do what we can. So I'm just going to split them out, and the goal is to just have in and in like that. Wire thickness is another thing that's quite interesting, and I mean, again, hopefully you can hear my dog barking now. Again, I'm not an expert with this, but I haven't had issues. I did do some calculations to work out what the wire thickness should be, and I got some thicker wires for the power, but I actually haven't found that it really matters particularly. So that's useful. Give me a couple of seconds, guys. Sorry about this. And I'm back. Sorry about that. We were talking about wire thickness, weren't we? So yes, it typically doesn't matter on this project, but as I say, once things start to get a little bit more intense, once we start doing more with the animations, it might end up being a factor. But I find this one's a lot easier to work with, and it does seem to be fine for the setup that I have. So I'm just going to go through. And I'm going to solder in these wires. What we can do is we can loop them through the header holes here, and then they should anchor a little bit better. You just got to make sure that you twist everything really well, otherwise it becomes undone. If you guys have any questions about anything while we're doing this, feel free to send them over. So what I could do with this is potentially twist these two together and just have them in. It's a very odd way of doing all of this, but I mean, for what I'm doing for a prototype, it works all right. Something like that. Hopefully they'll both fit through just about. And I'm just bending them over a little bit just to help them stay in place while I apply that solder. And then again, don't do what Dan does. If you're looking to get a soldering iron, there's a lot of really good options out there now. And this one that I got was very old, and the tip is really not the best shape for PCB work, unfortunately, so kind of making do with what I've got. So you can see we have the battery connector, we have the USB-C, we have the switch, and then we have the input. So again, this is going to be taken, let's assume 12 volts, into the buck converter. And then based on what we change this to, it's going to be outputting whatever voltage. And the goal here is to make sure that we can track that. And we'll probably use that later in order to understand what the setting is, because I can take this piece and connect it and work out what the actual voltage is. So we might do that straight afterwards, but let's finish soldering these ends in. So I'm trying not to lose too much length on the wire, but obviously they are going to have to connect there anyway, so we might as well just do it like that. So I'm just going to kind of roughly work out how far things need to be. And I'll just snip that one and that one. Give it a little bit of space. It's been great to see the interest that everybody's got in the project, and I've particularly enjoyed hearing about the people who have gone and built it themselves or are working on building it themselves. Because that's obviously, for me, that's very inspiring to keep working on this when it has been difficult to keep the motivation going for years now, to try and go through this whole project. It started out, for those of you who don't know, it actually started out as a box. It was a cube, and the bottom of the cube would detach from the top and it would kind of pop out, and then it could articulate. So that was the goal, was to make a cube that was, you know, could gesture and could interact with people. And all of the internal electronics have to be inside that cube around the mechanism that it articulated through, and it just ended up being awful because there wasn't enough room for anything, and what's the word? Linear actuator just didn't work well enough, wasn't strong enough, that kind of thing. So then, when I was looking for a new idea of how to do it, I started playing Star Wars Jedi Fallen Order, which I think most of you are aware that this is inspired by, and obviously saw BD1 and thought, that's what I want one of him. And of course all of the pieces fell in place because it was the same basic idea, really, was something that could be perceived as quite lifelike. And so that was what I did. Nowhere near as well built, but yeah, there you go. So okay, so I've connected the output there, and you can see now, if I was to take this and just jam it in because of the spacing, it would probably work. There you go. So I could say this should read the voltage of whichever thing it's connected to on the positive, and then obviously connected to the ground as well. So if I did it on that side, then technically it's going to be connected to that original voltage, so we should see whatever voltage that is. And what I can do is I can mess with my benchtop power supply here. I'm just going to take the voltage down to 12 because that's really what we're working with normally. I know you can't see this, sorry about that. And then I'm going to connect the battery input to that 12 volts. I'll turn it off just so it doesn't explode in my face. I don't like connecting wires when they have active power because I feel like I'm going to do something wrong. So in theory now this should read 12 volts, and in theory nothing should explode. And it doesn't work. Because the switch is off. Okay, that's good. Phew. So I'm changing it and turning it that way. That is 11.9, which is, yeah, it's about right. These things are quite cheap, so they're not going to be perfectly accurate. You can see we've got a power light on there. This is the first time that I've powered this up. Nothing is hot, which is good. And then basically what I'll need to do is go through and change the output, because I haven't touched that yet, to be something other than what it is, and I want it to be 5 volts. So I'm going to just turn that over, and again, breaking my rule of not plugging things in while they're live, I've got the 5 volt on the outside and the 5 volt on the outside, and then the ground in the middle. So as long as I line this up right, then It's just outputting the voltage that's the input voltage, which is probably because nobody's configured it yet. So what I'll do is I'll just take my screwdrivers and I'll have a bit of a play and see if we can get it down more. I'll point it so you guys can see. So we've got that currently 11.9, and then all I'm going to do is take this screw on the top and just adjust it. And this sometimes can be really fiddly, but as I change that, I'm screwing anti-clockwise and there's no change, so I'm going to screw clockwise and there's still no change. That's good. And the danger here is doing it too much. I was hoping to see some change in one direction or another. I do have the output wired connector correct, and I have that correct. So it should be doing something. Oh, there you go. Phew, okay. So we're taking it down, and as I turn it, you can see that voltage change. And we want it to be 5. I'm not going to worry about load dropping the voltage and that kind of thing for now. It's never really been an issue. So I'll make it 5. That's good, and that's actually a lot easier because that smaller one, if you touched it, like literally as you removed your screwdriver, it would change the voltage. So it was really finicky, if you understand that word. So that is now set to 5 volts, which means we're safe technically to put that into the Arduino, to put that into the servos. And what we should see is if I take it out of the output voltage and into the input, the original voltage, you should see that is still the 11.9. What we should also see is, by the way, if I increase the voltage on the benchtop power supply, I'll make it 20. We could make it 24, couldn't we? Because that's what we're testing at the end of the day. So this is the maximum I want it to. Yeah, okay. Benchtop power slice is 24. I'm happy with that. So the original voltage is 24, and then I turn it over, and then this one should still be 5. And again, a little bit of a margin for error, but it's not going to do any harm, that extra, if that's actually what's being output. So the good thing is that it can accept anywhere from over 5. There is a point at which it doesn't work efficiently enough to maintain the voltage. So typically I would pass in at least 8 volts and then ideally 12, but that means that as the battery increases or decreases, you're going to get that consistent 5 volts out. And because it's got the capacitors and the other kind of components that the smaller one doesn't have, it should work a lot better than the original. Sorry, it shouldn't cause you any problems if the voltage changes too much. So that's that. So let's turn that off, and I'll disconnect that. We'll do that again later. That's probably how we'll test it, to be honest, but we'll do that further down the line. So that's the power, and basically all I care about now is getting that connected to this and how that impacts everything that we have in place. So again, because we've got that JST connector, I can just plug that in. It won't accept it that orientation, but if I turn it over, it should accept it that way around. Now what I'm going to do is I'm going to take this guy out because I really don't have a spare one, at least not one that's not already soldered to a board, and I absolutely hate desoldering ICs. So I'm going to leave that one disconnected, and I'm going to test some stuff as we go and just make sure that it kind of does what I expect it to do. And then we'll wire up this thing to the actual output and so on and so on. So actually what I could do is still have that connected, and I will break my circuit on live TV, which should be nice. So now that's 24 volts. I'm going to drop it back down to 12. And I'm going to get my multimeter, and I'll just talk you through how we do this. Again, this is useful if you haven't done this yourself. So there's a question. What's the name of the voltage tester? I don't know, but honestly, I've had a few, and if you just search for like voltmeter component on something like eBay, you'll find it. I also have a circular one that's quite big. Bigger than I wanted for this project, but if you're building something like an R2 droid or something, it probably fit quite nicely. There's a lot of different options available, and you can pick the color and so on and so on. But yeah, I think I just search for voltmeter component and it typically comes up. And there is a dial on the back of that, which I've never touched, but I think it changes the range or something, but you don't typically need to adjust it. I'm not actually sure what that one does. So we should be taking 12 volts in now through the yellow wire and 5 volts through the red. And then that means what we should be able to do is see that some of these things are live, are connected. So I'm going to take my multimeter. I mean, if you haven't used a multimeter before, this is probably not the course for you. But it's well worth getting one, and getting one that actually has a decent range. Again, this is an old, cheap thing. You're starting to notice a pattern here. Most of my stuff is quite outdated. I guess that's good. You can see that you can do this, even though that's the case. So I'm going to set it to voltage. I'm going to set it to a range. It's not going to be more than 20, so I'm going to set it to 20. And then what we're going to do is just have a look. So I've got these pins in the middle should be connected, I think, although we might need the Arduino in place for them. That's probably the case. So let's check first of all this one, which is the voltage output. And I want to do that because I'm going to connect that voltage meter to that area. So I'm just going to put the negative on the negative and the positive on the positive. And there you go, and we can see 11.96. So that's pretty consistent. This is for the Raspberry Pi. I'm not connecting those today. I'm not so worried about that. And then, as I mentioned, for these ones, this is standard servo connection where the inner row is to the pins, and then we've got the ground, we've got the voltage, and then we've got the ground. So in theory, if I actually touch any one of those middle pins, be really careful here, because if you bridge them with the thing, it can cause some harm. So I'm just going to touch the middle, and then I'm going to touch one of the outer ones, and we should see that coming out as 5 volts. So you can see the 5 volt rail on the board is active, which is exactly what we want. Now, out of interest, if I was to touch these middle ones for the other component, see, that's not in place yet, and that's because it has to run the power through the pins on the Arduino, and that's fine. The danger with doing that is if you're powering the servos through the Arduino, then obviously that's a bad thing. But this measurement component is such low power, it's not really a problem to do it that way. Next version of the board, I'll probably make it so the power comes independently, but you are a bit limited on where you can run tracks, so you've got to be a little bit careful with that. What else? We've got the voltage divider, so what I want to do there is just check that I guess we're kind of okay with that for now. So the next thing would be to connect this so I can see when the board is active. I really don't want to do that without knowing, so I'm just going to turn this off, save the battery, and then we'll disconnect this guy, and then we'll swap the wires out on here. So I'm turning that board off, again, just for the sake of safety. I don't want that DuPont connector on the power board anymore, so I'm going to swap it out for this. And again, it's about how much space to strip on these things, because it can get a bit messy if you take too much off. This is where I'll be picking up little bits of wiring insulation out of the floor for the next week. So I'll use this to hold on to it in here or in here. Let's do it like that. There we go. Okay. And then I'm going to take this guy off, and I just have to remember that the negative is on the outside and the positive is on the inside. I made that mistake before, and the soldering iron is quite hot, so it should disconnect quite quickly. There you go. And you can see on this one actually the positive kind of has 2 and the negative has 1. So let me tin these first, which ideally I'd use the helping hands for, but I've done this in the wrong order. That guy on there. And it really doesn't take very long. The only thing you've got to do is be careful that you haven't connected it to any of the other pins, which is one of the risks. And this is such a tiny thing that it's quite easy to do. And then what I also sometimes do is just grab a pair of tweezers just to hold all of this in place, and then I'm not burning myself, which is always good. There we go. Again, if you're buying wires, silicon wires apparently are better because they don't melt as easily. Let me just check that that's not touching anything else. That looks okay. So now in theory I can plug that in here. Again, it will only accept that other orientation. I nearly got it wrong, so that's useful. And now if I plug the board in, we should see that that reads out as the original voltage, which should be 12 volts. Yes, good. That's what we want. Next steps. I'm probably going to connect, there you can see that dying off there. I'm probably going to connect the Arduino now, because there's very little else to do on this, and then we can test it by putting a servo in and just seeing whether it's actually moving that servo around. I don't think there's anything else I can do to test this. What I'll probably do though is take that header pin off so you can see how that works. So sometimes if this isn't lined up, these female headers are really cheap and not the best. They sometimes make it quite difficult to get things in, and also I've got that one, so I'll pull them out just for now. There you go. So yes, you can see this row isn't connected. This is purely going to be for programming, and then there are multiple pins that handle the same thing. So there's my pointing tool. There's a TX and RX over here as well as up here. You've got voltage, which is also over there, and you've got ground, and there's a ton of grounds kicking around on most of these boards. So the goal is that, you know, the ground for the Arduino is connected through that one. I know that because it's traced back to here, and then the voltage is connected yeah, via this kind of under the board. So we know that all of that should work. We're not going to worry about the TX and RX on this one because, as I say, because this board is broken, because I made that mistake, I'm going to have to go and wire that in manually, which I will do, and then it means that when the new replacement boards come, I can pop this off, take all of those off, just resolder some of the headers and the JSTs, which is not a big deal because they're not expensive, and then I'll swap it out for a working one. But yes, what I should do is if I take this off, and this is that bridging header pin, which I don't know what they're called actually, but all it is a piece of metal inside, so it joins the two pins together, and you can see we've got the two exposed pins down there. So now if I turn it on, there shouldn't be a light on the Arduino because there should be no power. If there is, I've done something wrong. I'm going to stop there and sit and figure out what's going on. And there's no light, so that's good. So again, that's still reading 12 volts. I'm going to turn that off, and then I'm going to connect this, and then we should see the light on the Arduino, and then because I've already programmed it, we should see there's another flashing LED which indicates that it's trying to move servos, and that's just a bit of a debug output that's been in the beginning, since the beginning of this version of the project. Oh, yeah, go on then, let's do it. Good. Ish. There we go. So the flashing is, I'm set up, I'm good, I'm trying to move the servos to their initial position, and then I'm doing the animations and things like that. Now, I'm not going to show you guys the code in this because it's obviously a little bit difficult to switch between the laptop and so on, but there is code on a branch that is specific to me integrating inverse kinematics with the project. And once I've finalized all of that, I'll share that as part of the main branch on the project. So there you go. So I guess the next thing is going to be to try and attach a servo. I'm not going to use the robot because I really don't want to break anything on there, but I do have some test servos, and I have a one that doesn't work very well. So if that gets fried, that's not a problem. So let me grab that. Get rid of some of this stuff. So what do we have? We've got a couple of these. One of these things is not like the others. We've got all of these are knockoffs, I think, and then there's one that doesn't look the same, which is that one, and this one I think is the official one, but it actually is much more jittery than the knockoff ones at the voltage that I use it at, so I actually don't use this for anything other than testing. So again, checking our orientation, we want to make sure that things work the right way. So for D2, which is one of the neck servos, and again we want to have it that way round, and we want to plug it in and not join to anything else. And you can see it's going into a position there. If we waited long enough, you could see that this would probably move, but I don't know how long it'll take. I can't cycle through the motions, so I'm just going to quickly run through and just check that it does adjust this for each of the connections, and that kind of implies that things are wired up correctly at least. Yeah, and I mean, you know, with some luck we'll see it moving because of the flashing light as we go, but that doesn't always work out the way. There you go. That's that one. So then, as I said, these are all connected perpendicular to the Arduino, if that makes sense. And if these were straight up, they would be as well. But because we're connecting it at 90 degrees, we actually have to kind of be mindful of the orientation there. So for example, if I was to connect them that way, it would just connect all the grounds together. So this is the orientation that we need, but we want to make sure that the signal pin is inside. So then it's the top row that are being connected, and we can see that works, or at least initially. And then check the same for the middle one. That's moved a little bit, and then the bottom one as well, and that was the big one. And for the legs, you should see some motion as you're testing this, because it is going through and actually doing some stuff and making some changes. But it depends, because the script can, you know, do what it wants really. So this side, that's good, and then this one, and then that, and that's everything. So that all looks pretty cool. I'm quite happy with that. What I need to do is put it in the project and connect the legs, but I am going to take my time with that, because if I connect the wrong one and it thinks it has more range of motion than the hardware actually does, then it means that we end up with pretty big problems, because it can break the motor, or it can break the 3D print or whatever. So I'm going to double check and triple check all of that, and I'll do that all offline. The next thing is around the voltage divider, and I wanted to just show you the last piece of that, just to make sure that you kind of understand how that works, and hopefully that benefits you and you can use it in the project. It's really quite simple. I have the two resistors, and as I mentioned in my diagram, these are 8.2k for the first one connected at the 5 volts, and then 2.2k for the one connected from the midpoint to the ground. And the reason why they are those values is because that's what I have, and it actually doesn't matter a huge amount, as long as you've got the ratio correct, and there are calculations you can do, and you can use calculators online. The goal is to get the output voltage so that at your maximum input, the output is less than the maximum the pin can handle in the Arduino, which is, in my case, is 5 volts. It could be a 3.3 volt device, or you need to be lower, and so on. So you don't need these. What you need is a ratio to be correct. The only thing I would say is, I did try it with some very low resistance ones, and I released the magic smoke this morning. So you obviously do need to make sure that they're high enough resistance that it doesn't just allow all of the power to go through them. I think that was like 38 ohms or something, and I thought, I'll give it a go and see how that works. So the 8.2 is that one, 2.2k is that one, and what we'll do is we'll just connect it, and I'll show you in practice how that works. Double check that I've got the right ones, and then that way we should be able to take them out and put them in the circuit board. So I'm going to turn this off because I need that power. It's a shame I can't just plug that into there. If I had another connector, I could probably do exactly that. So let's get rid of this for a second. I'm going to take the power out of here. I realize you can't quite see this, but that's the power that I'm connecting to. And I'm going to put it in so that the positive's on the left. And then when I turn this on, obviously nothing should happen, hopefully. This is 12 volts. I can see it's not really reading any amps at all, so it's not drawing any current other than a very, very small amount. And then what I'm going to do is grab this, and I'm going to put it on voltage again. And where you want to connect is between the midpoint, which is where they join, which is just here, so either of these legs will do because it's all just one big wire, and then the ground, which is the other side of the resistor. And you can see there that it's reading at 2.52. Now that means if it was at 24 volts, which is double, it's going to be just slightly over 5 volts. And the Arduino can handle a little bit more, because I accidentally fed it more in the first version than I realized, and it did it for a while without complaining. So like 0.0 something volts extra is not going to be a problem. So yeah, I'm happy that that can cope with more than I'm going to use. As I say, it can deal with about double, but it does mean if I need to use USB-C and it needs to be 20 volts, because that's all the USB-C power adapter will supply, then I'm comfortable with that. So now all I've got to do is be a bit careful that I'm taking the right resistor and putting it in the right place, and the right place is going to be in here. But first of all, I'm going to disconnect my precious Arduino and make sure that I'm doing all this right. So if we look at this board, because it's a bit easier to see, the input, there are 3 inputs. We know the middle one is ground, we worked that out earlier, so this is the input voltage, and then it goes into that pin through the resistor. There is a join here which also feeds off to A0, which is that one there, so that happens underneath the board, so you'll not be able to see that trace. And then the second resistor takes it back to ground. So we know this is the first one, that's the 8.2, and then this is the second one, which is the 2.2. So I'm just going to grab my 8.2 and put that in there. Obviously that's 8.2K. I haven't given them a lot of space here, but that's because actually I needed the room for the tracks. But it doesn't really matter because everything else is a bit bulky anyway. I'm just going to pull it through a bit. I don't want to force it. But this is still a hell of a lot better than the original one that I did over there, which had wires and all sorts hanging off them. It was awful. So I haven't got the fan on, but I'm just doing a couple of them. I'm just going to be quick. And those legs, once you're done with it, can just snap off because you don't obviously need them anymore. You don't need to cut them, they can just wiggle off if that's what you prefer to do. So we can see there, hopefully, I haven't done a terrible job of that. And then the 2.2 goes on the other way, and I'll put them in the same angle so it looks a bit neat. But yeah, I got a pack of resistors years ago for a project where it just had mixed values, and they were all unlabeled, and I don't know how to read resistor color codes without a guide, so I have been working through them with my multimeter, just working out what the voltages are, sorry, the resistors are, and then labeling them and then putting them in the right hole in my box, because it means that then at least next time I can come back and use them quite quickly. So I did quite a bit of that this morning while I was waiting to come online. And obviously, in case you're really new to all this, there's no orientation to worry about with resistors. You can't, there's not a positive and a negative end. So that's that, and I've plugged them into the wrong board, haven't I? Oh dear me. Don't put them on your test board, put them on your actual board. If that's the only mistake that I make, we're doing okay. In fact, I can get some more. Let me get some more, and then then we don't have to learn from our mistakes, so that'll be good. 8.2K and 2.2K. And I'll desolder the other ones later, or add them to my desoldering pile, which is which is getting big. I absolutely hate desoldering things because I'm no good at it and I just don't have the right tools for it. So if you guys have suggestions or equipment that you use, then feel free to let me know, because I hate the fact that I've got boards that I can't use just because they're connected to an old project. I don't like using these female headers, but I don't like desoldering more. So there you go. Put that one in there, I'll just solder him in. And then the 2.2K, which is the other one on the other side. This is, as I mentioned, this is the first time I've done the live streaming on Instagram, so I'm hoping this will all be something that I can save out and share on YouTube. So if you're seeing this on YouTube, hello. If you're not, then hello. Put a little bit more in. There you go. So that's that. So what's left on this board, we basically got those in place. I'm going to give them a test next. Then the motion, or the sensor is going to go underneath like that. Let's get rid of him so I don't get confused again. But I'm not going to do that on this one because I know I'm going to swap this board out and I actually don't have anything to test with that yet anyway. So that's fine. I'll do that another time. Get rid of these really quick. That, and then yeah, so we need to test it before we apply the Arduino again, because if A0 is reading a ridiculous voltage, then I've got my calculations wrong somehow, and obviously we don't want to break anything. So I'm going to take my 12 volts, I'm going to plug it into my power again, check the orientation, and we're good. So I'll just plug it in, and it's showing there as 11.9. And then what we should see is A0, which I'll have to get at from the other side. Should be A0 and ground. Where's my taser? So I know this brown wire is a ground because that's because that's the one that I soldered in place, and then A0 is one of these, and it's going to be 2 down from A4 and 5, so there-ish. Tell you what, let me connect that. That's it, yeah. So that is 2.53, which is what I expected it to be at 12 volts. So I'm pretty happy with that. So that means when I plug the Arduino in, it's not going to do anything because it doesn't actually have that code in this version, but I did in an earlier version, so it should be all right. So again, I'm going to kill the power, and then I'm going to plug this back in, and then we should see that that's all working pretty well. And what I'll do is I'll stick one of them in beforehand, and we'll hopefully see some activity on the legs. Now the biggest one that moves is probably going to be the middle, so let's put him in there, and then with a bit of luck you guys will see as this gets plugged in, you should see it doing something at least, and then we'll know that it's hopefully all right. So that's in place. We've got the power coming through from there. We're not going to connect the Raspberry Pi, and then we'll give it a test. There you go. So it's set that initial position, and obviously normally there wouldn't be as much of a jump to the movement there because that initial position is actually going to be more or less where its resting position is. So it should maybe jump a little bit because the power's in place, and then kind of go from there. So I think that's everything. There was something else I was going to say as well, and I can't remember what it was. But yeah, the next step's going to be to obviously put this all in place on the project, and then I'm going to do some 3D printing. So the next part is going to be to take, come over here again please, there it is. It's going to be to take these pieces, which were very much temporary, and the standoff screws and so on. I'm still going to use the same format because I still want it to be modular, I still want to be able to reconfigure it, but this piece, as you can see, was bolted on to a thinner hip cradle, if you want to call it that. So I'm going to try and improve on that design, have this a little bit more finished off so that when I have the power board in here, because the goal is that this piece is going to go in there with the switches on the back and the plugs on the back, and then the wires are going to come up to the top part, and the top part's going to have that piece with the power management on, and then inside that we should have the new version of the board sitting in the same place, and you'll see there should be exposed elements as the head sits on top, there should be an exposed part to allow these to come out, and then also if I need to program it, I want to be able to connect in there as well. So I've got to do a little bit of work, because this was just a kind of generic add some spaces to allow it to do that, but actually it can be reconfigured, and I'm going to make it so that it's specific to having gaps for these things. And then on the side, what I did have was something that slotted on there and had holes in so that you could pass the wires through and have it looking quite neat. I did wonder whether it was going to be wide enough that you could actually have just the square holes for putting all three of the DuPont connectors in, but it doesn't look like it will. So the whole point of this was to get this to the point that it was all much more slim compared to the original blocky green one, and I can slim this top level down a little bit, and then I can make it so that it all works quite well. The only thing is the limiting factor on space is this, because it's a huge block that needs the width and so on. But I'm not going to worry about that for this version, because perfection is apparently the enemy of progress, as my personal trainer told me years ago. So there you go. Does anybody have any questions? Is anybody still online? You've done very well to stay through this whole thing to the end. I think one of the things to mention as well that I haven't had a chance to talk about fully on any of the shorter videos is around why I've changed this to focus more on the Arduino. So originally, the serial connection to the Arduino was the only thing that made the Arduino move. So what you would have is you would have the Raspberry Pi would boot up, and it would take, minutes sometimes for it to boot up and get to the point where the code was running. And then assuming that process all happened correctly, you would then get a signal from the Raspberry Pi to the Arduino to say, move the legs to this specific position, get it all sort of sitting, and then it would stand up. And those commands, those positions would all be stored via the Raspberry Pi. The Raspberry Pi isn't ideal for that, and really ideally it should be delegated to another controller. And then the other side of it is that because that boot time was so large, you ended up where you had to wait. Somebody said, oh, show me the project. You had to wait for the whole thing to boot up before you could even just get it to stand and do some basic animations. So to really utilize the power of having an Arduino rather than just a servo controller connected, what I wanted to do was make it so that they were a little bit more independent. And that's good, because if somebody wants to build this and they don't want the Raspberry Pi, which I can completely understand because it's been a nightmare, the whole process of programming and configuring the Raspberry Pi has been a pain compared to something like this. I still haven't got the the speaker working. The microphone configuration took me about a year to get working. Like, I get that you might not want that hassle, and you might just want something that you can control yourself. You can just have an Arduino, and you just leave this connection off to the Raspberry Pi, and then everything works, and it animates, and it does what it needs to do. Whereas that never used to work before, because it had to be getting those signals from the Arduino. The other thing is, if you want to take it to an event, or you want the battery to last longer than, I don't know, an hour or whatever it would do with the Pi running, you can do that by just disconnecting the Pi and then having it so that it still kind of looks like it's moving around. The only reason you could tell is that it's not going to be doing any of the facial recognition stuff or the noise or anything. But the eye would be off as well, because it's a NeoPixel that's powered via the Pi. But it means that, for the casual observer, you want to show this thing off, you want to take it to a convention, you want to do whatever, you can do that all with the Arduino, and the battery would last a hell of a lot longer. And then the final thing, which I'll get to now, is I don't want to limit it to a specific system. So we've got a guy who's building one of these in Turkey who is using a Jetson Nano, I think, and instead of the Raspberry Pi, which is great. You might not want the hassle of programming it via the pins. You might want to get an Arduino Nano, which I used for years, and they were totally fine. I did it for space saving, but actually, arguably, it hasn't saved any space when you think about the orientation, the form factor of this. Pi Picos are really accessible now. This is the first one I've ever bought. It's Wi-Fi enabled as well. And so when you you know, if you just want something that you can control yourself, and I get a lot of questions from people asking, is it something that you control or is it something that's automated? Now, my goal was to make a companion. It wasn't to make something I could press buttons on. So it is fully automated. But, it, you know, saying that, it doesn't do a lot unless you put a lot of work into programming it. And the voice recognition works all right, but, you know, if the room's quiet and so on. If you wanted something that you can control yourself, you've got Wi-Fi enabled boards like this that mean you can connect to it through your phone or through a Bluetooth controller and puppeteer it, basically. So what I wanted to do was make it so that there were a selection of boards for different projects, for different controllers, and make it so you guys could basically do whatever you wanted with them. So this one is Arduino Nano, this one is Pico, it's the same thing. You can see we've still got the Pico, we've still got a power board. This is the goal for this one, is to be a standalone, slightly smaller one, so you don't need the Raspberry Pi, so you just power it. And then you've got that same bridge connector if you want to do for these, and then you've got all the servos. And these things, because we can make them easily and they're quite cheap to produce, it means that we can have a selection of them, and people can contribute to them. And the repository is available if you want to fork it and then make your own code or make your own boards and share those boards in the repo, then other people can get access to them as well. So the goal with this was really just to make it so that you could do whatever you want to do with whichever technology you have kicking around. You know, if you don't want a PCB and you just want to do it yourself with wires and breadboards and whatever, then really, why not? You should be able to do that. So the goal here is to make it so that all of the components are optional, and then we take it a step further and we kind of get people involved. So that's the idea. I'm going to work with this version for my next, like for this version to complete it, and then once that's in place, I'm going to take a look at whether I can maybe build something slightly smaller with slightly smaller servos, but that might be further down the line. But if there is anything you'd like to see, and if you'd like me to explain anything in a little bit more detail, then obviously let me know. I'm trying to think back to questions that people have asked, because there's been a lot of questions coming in on Instagram, and it's difficult for me to kind of respond to everything. I typically don't see everything. I think I'm aware that that's the case. So yeah, maybe I'll take a couple of minutes just to see if I can think of anything else, and then we'll call it quits. So feel free to fire over some questions if you've got any, and I'm going to kill the power on this before I accidentally touch two wires together and fry all of that hard work. So, as you know, this is the body, this is the head. They are designed to be independent. I appreciate that's not all on screen for you. Apologies for that. Maybe I'll turn them this way, and then the portrait people can have their fun. There you go. So all of these things are using readily available hobby servos and equipment. So everything is 3D printed in the leg, apart from the hobby servos, the nuts and bolts, which are a standard diameter, and then the bearings. There are two bearings for each joint, and these are skateboard bearings, so they're actually designed to be completely easily available. You can get a hold of them on eBay, you can get a hold of them on proper bearing sites. It's not a big deal. And it uses the same type all the way through. These components, these 3D printed pieces, are designed to be identical. So there are actually, for the leg joint, there's 1, 2, 3, 4, and then 5, 6, 7, 8 of the exact same piece. So if you break one, you print one. You don't need to worry about which piece you need to print. The same with the gears. The ratio of the gears is currently 1 to 1 because that works for me and it made it easy to calculate. But if you're carrying something heavier and you're not bothered about having the full 180 degrees range of motion, you can print a 2 to 1 or any kind of variation you want. You just need to redesign these kind of dark blue parts and print those again, and that would give you the change that you need without having to reprint the whole leg. The hip joint is, as I mentioned, articulated. There's a tiny bearing in here, which is the same kind that we use for the neck. So you just need a pack of these little bearings. I can't remember exactly what the diameters are, but I mentioned it in the video on the leg build, which is on YouTube. Get a pack of them, cost nothing, and then you've got access to put those in here and here. And again, the nylon spacers and nylon screws, you get a pack of those for, you know, $10 or whatever the equivalent is. And then That works for the body, it works for the whole leg mechanism. There's actually a spacer between the two screws in the hip that pin that together with the bearing inside and so on. So it's all designed so that you don't need to go and source 100 different things. You can just do it all with a few pieces that you have handy. And again, that's why we're trying to make this stuff more modular as well, so that you guys can go, well, I don't have that, I have a different board. But that's not a problem, because all you've got to do is solder the wires to that board instead of another one. Whereas when it was all integrated into the PCB that we saw at the beginning, that really made it difficult. You know, picking the right relay board when we had that in place was hard, because the one that I had wasn't even standard. I had to modify it to get rid of the screw connectors and put it into PCB headers instead. So it's all about making it accessible to everybody. That's why it's as straightforward, hopefully, as it is. That's why I've made certain design choices, so it's not the best it can be, but it's accessible and it's easy for you to use. Things like this, where there are different mechanisms that you can use to control the head, and this one's a bit loose because I can add spacers in this joint and firm everything up, but I'm not ready to do that yet because I want to make sure as I'm testing that I'm not jarring anything and so on. So there's a lot of flexibility that goes through all of this. And then anything that isn't one of those spacers is going to be one of these tiny little screws that attaches the servos. And again, this uses those same nylon screws. These don't, because they're too the hole's too narrow. So it uses I actually can't remember exactly which one they are. I haven't got them with me, but it uses screws that are typically available and come with the servos that you buy. And if they don't, the holes are so small that you can use a different screw that comes with the servo. It's like, it doesn't have to be prescriptive. And again, the neck, this one here has a standard bearing the same as the legs, so you get a pack of them, you're good to go, and it all just works. And the head is exactly the same thing again. So the only thing that you really need to buy and build custom is the PCBs. There's a PCB attached to the Raspberry Pi, and then there's the PCB that we built today, which is for the arduino. And again, arguably you don't need to do that. It just makes the whole thing more straightforward for you, because if you need to attach some servos, you cannot power your servos through your IC board. You have to power it through the main power supply, and therefore having a board that allows you to do that just makes things a lot easier for you. But yeah, I get people some people don't have the ability to print these things, or they don't have the knowledge to print them. Some people don't want to have to do the soldering, which, you know, that's fair enough. It might be that, you know, if you need the boards and someone is willing to help you out by supplying you with the pre-soldered boards with some headers and some female headers so you can attach your IC, then that would be great. And obviously if people want to connect over that, then that would be great, and I'd be happy to facilitate that kind of thing. So there you go. I think that's everything, and I think everything's kind of been covered in videos. But if you do have questions, let me know, and I'll try and do some more of these in the future as I'm building different things. I don't often get the chance to sit down for a long time and do something like this, but yeah, glad that I could walk you guys through the changes that I've made, and hopefully the next video that you see will be this working with its new board with a few 3D printed parts. Thank you very much. If anybody is still online, all the best. Enjoy the rest of your day.